Here's a Newton's law problem that has a block up against a wall. And someone is pushing on the block with some force F up at 45 degrees like this. So what the problem wants to know is, what would this force have to be so that this block can slide down the wall with a steady speed? Now you have to read those words carefully here, because once again the word steady here and steady speed implies the velocity steady. That means whatever v you choose as to go down isn't going to change. And steady v means that a sub y is equal to 0. So whether you choose 5 meters per second or 10 meters per second, however fast you want this block to descend, if you want it to stay at that same speed, the y acceleration must be 0. The other thing that I notice about the block is no one never said anything about it crashing into the wall this way or flying off to the right, or even if it started to do that, that would violate this steady speed thing. So you can also sort of assume here that a sub x is going to be 0 too. So we have a situation here before we've even started, just by reading the problem, that we have two components of acceleration which probably need to be 0 for this problem here. This guarantees a steady speed going down, and no one said of anything about it crashing into the wall or flying off wildly to the right, so the y acceleration, the x acceleration is going to be 0 too. So both the x and y accelerations are 0. The reason why that's helpful to us is because the guiding equations that we have on this box here say that the y acceleration is the sum of the y forces divided by m, and the x accelerations are the sum of the x forces divided by m. Those are sort of our guiding equations that we have going here. And if both of these equal to 0, this is equal to 0 and this is equal to 0, we're left with a case here for the problem where the sum of the y forces are equal to 0 and the sum of the x forces are equal to 0. So these two things, before even analyzing the problem very deeply at all, we already have some guiding equations that we can use to solve this. So what we need to do now is return to the problem, since we're going to be summing forces, and see if we can identify the forces that are acting on this block. Well, we know we have this one here. This one has two components. It can have a y component this way and an x component over like this. This component is going to be f times the cosine of 45. And this component over here is going to be f times the sine of 45. So we have two components there, and we can use trigonometry to find out what the components are. There's two more. Well, there's several more forces on the block. Let's see if we can identify them. We have a normal force because of the surface is being deformed, because the block is being pushed up against it. So we do have a normal force here. That's the molecular flexing in the wall here. We do have weight of the block down like that. We'll label that mg. And lastly, if the block is going to move down like this, then we will have a frictional force pushing up like that. There's plenty of forces on the block. So we won't get intimidated by that, because we have Newton's laws as our guide. These are the raw ones right here, but we have processed them down just a tad bit here to make it more specific to the problem. So why don't we just start using them? Why don't we sum the y forces on this block and set them all equal to 0? So one y force I see is the friction up. Another y force I see is the weight down. F minus mg, and I'm sort of observing a sign convention that up is positive and down is negative. And lastly, I also see an upwards component to this unknown pushing force right here, which is f times the sine of 45. So that would get added in there as well. F times the sine of 45. So we have friction up, weight down, and we have that upwards unknown pushing force up like that. All that has to be equal to 0 because of what we discussed here about the acceleration being 0 for steady v as the block goes down the wall. So you can put a big box around this here and go, yeah, you just found yourself an equation in there. You've got it, okay? Something you can solve for. No answers are going to pop at you because you don't know the frictional force and you don't know the pushing force, but all right, you have an equation. Why don't we drop over now to the x-axis and see what that gives us? If I look at the x forces, I see a normal force to the right, and I see a pushing force to the left. That looks like about it for the x force. Let's see if we can put that together here. So I see a plus n to the right, minus an f times the cosine of 45 over to the left, and all that's going to be equal to 0 because of the steady speed constraint of this problem here. So we have another equation here. So really, we're sort of done analyzing the problem. Look, we've used both Newton's laws in two dimensions, both x and y, and we have these equations for them. We just need to drive home our solutions now to see where the solutions are going to come from. So you look carefully, and this is going to be pretty typical of a lot of these problems here, is that the frictional force, remember, is mu times the normal force. We have that in there. So you can rewrite this equation, sort of filling that in. Mu times the normal force minus mg plus f times the sine of 45, all that's equal to 0. So that equation sort of gets morphed into this mu times the normal force now. And now what are you looking at? Well, you have the normal force from right here. So you can do a bit of algebra and actually get yourself one big equation. In particular, mu. If I solve this for the normal force, I'm going to get f times the cosine of 45 minus mg plus f times the sine of 45. All that's equal to 0. So I'm going to end the video here because I think the solution is at hand here. There's one big equation which you can solve for f. The only unknown in this equation is F now. I believe it was a wood-on-wood type of problem, so you can find the coefficient of friction for that in your problem, or if there's two different materials that are quoted in your problem, you can use those. Cosine 45 is known. The mass of the block was known to be some number, and G is 9.8. So you know everything. You can just solve for F. And that would be the force at which this unknown force is going to have to push on the block in order for it to lower at the steady speed indicated. Nice problem.